Hello and welcome to the Analog Devices Precision Technology Video Training Series. This video will focus on some key considerations when designing front-end ADC driver circuitry for the LTC2387-18. The LTC2387-18 is a SAR, or Successive Approximation Register ADC. A sampling rate of 15 megasamples per second can provide benefits in closed-loop systems measuring high-frequency signals, or where a fine time resolution is required when profiling signals in the time domain. The LTC2387-18 has Nyquist sampling up to 7.5 MHz. Delivers signal-to-noise ratio up to 95.7 dB and total harmonic distortion performance up to -101 dB, and specifies 3 LSB maximum INL performance. The Precision ADC Driver tool, which can be found on the Education section under Data Converter Tools in Analog.com, will be used to highlight the key recommendations when designing an ADC driver circuit for this ADC. Evaluated are 4 different circuit configurations where the associated SNR and THD performance is obtained for each. These circuits will be analyzed assuming a 100 kHz differential input signal with an amplitude of 4.096 volts peak-to-peak, sitting at a common mode voltage of 2.048 volts. With the LTC2387-18 sampling at a rate of 15 megasamples per second. To achieve the best noise and distortion performance from the LTC2387-18, the first recommendation is to drive each analog input with a unity gain amplifier circuit. Selecting the LTC2387-18 from the ADC menu automatically shows 2 ADA4899-1 op-amps configured in unity gain. Looking at the Noise and Distortion Performance tab, the distortion THD is -113 dB and the system noise is 48.9 microvolts or ms. The signal-to-noise ratio SNR is projected to be 95.5 dB. This performance correlates with the ADC datasheet specification at 100 kHz, indicating that the ADA4899-1 unity gain amplifier circuits have very little impact on the ADC expected noise performance. The second recommendation is to add any signal chain gain before the ADC input driver buffers. To add a gain of 4 to the ADC driver circuit, select a non-inverting configuration from the driver section of the tool and set the gain to a value of 4 volts per volt. The ADA4899-1 is now fully configured for a differential input signal of 1.024 volts peak-to-peak, sitting on a common mode voltage of 2.048 volts. Non-inverting configuration with a feedback resistor of 100 ohms and OR-G of 33.3 ohms. Comparing with the performance achieved from Recommendation 1, if the gain is added to the driver stage of the circuit, the THD remains the same, while the signal-to-noise ratio is reduced by approximately 4 dB. and the system noise increases to 82 microvolts or ms. The third recommendation is for a single-ended to differential signal conversion taken place before the ADC driver input circuit stage. In the ADC driver tool, select the non-inverting configuration for the input driver circuit, with the gain set to 1 and the single-ended input. The circuit uses two ADA4899-1 devices to perform the single-ended to differential conversion. The distortion for this configuration is -112 dB, and the system noise is 54.7 microvolts or ms, with the associated signal-to-noise ratio projected to be 94.5 dB. The distortion and signal-to-noise ratio are both reduced by approximately 1 dB. The fourth recommendation is to use a fully differential amplifier, FDA, to drive the LTC2387-18 when power consumption is a concern. Select the ADA4945-1 fully differential amplifier from the list of recommended amplifiers, and set the input as differential. The ADA4945-1 has a quiescent current of just 4 milliamps. Remember to change the input to differential and the frequency to 100 kHz. The circuit shows the ADA4945-1 configured in an inverting configuration. Its output is connected to the RC filter, which then connects to the LTC2387-18. The simulation shows a distortion of -108 dB and a system noise of 100 microvolts or ms, with the associated signal-to-noise ratio projected to be 89.2 dB. Comparing with the performance achieved from Recommendation 1, the SNR is reduced by approximately 6 dB, while the THD reduces by 5 dB. The reduced performance comes at the benefit of 25 milliamp lower quiescent current versus the two ADA4899-1 buffers. In summary, optimum SNR and THD performance for the LTC2387-18 is achieved with a unity gain buffer ADC driver circuit. Adding gain or single-ended to differential conversion to the ADC driver circuit impacts on SNR and THD. Lower power consumption is achieved with a fully differential amplifier used as the ADC driver, but at the expense of degraded SNR and THD performance. The four recommendations highlight the trade-offs for each ADC driver circuit configuration when using the LTC2387-18. The implementation of recommendations will depend on what the application can tolerate. To learn more, please watch the next in our Precision Signal Chain Platforms video training series.